In 1896, Antoine Henri Becquerel unveiled a phenomenon that would irrevocably alter the landscape of physics. His paper, on the invisible rays emitted by phosphorescent substances, detailed an unexpected discovery arising from experiments intended to explore a connection between phosphorescence and X-ray emissions. Then a very recent sensation, Becquerel's initial investigations were heavily influenced by Wilhelm Röntgen's discovery of X-rays in 1895. The scientific community buzzed with excitement over these mysterious rays capable of penetrating opaque materials and exposing photographic plates. Becquerel, intrigued, wondered whether phosphorescent substances, known to emit light after exposure to sunlight, might also emit X-rays during or after their phosphorescence. The connection seemed plausible. Both involved the emission of energetic radiation. To investigate, Becquerel prepared an experimental setup employing uranium salts, specifically potassium uranyl sulfate. His method was simple yet ingenious. He wrapped photographic plates in several layers of thick black paper, rendering them impervious to ordinary light. Upon this shielded plate, he placed a crystal of the uranium salt and exposed the entire assembly to sunlight. If the uranium salt emitted X-rays during phosphorescence, these rays would penetrate the black paper and darken the photographic plate upon development. Initial results appeared to confirm his hypothesis. The photographic plates exhibited a distinct darkening beneath the uranium salt crystal, suggesting that the salt was indeed emitting penetrating radiation when stimulated by sunlight. However, a pivotal incident occurred during a period of cloudy weather in Paris. Unable to expose his samples to sunlight, Becquerel stored the prepared photographic plates and uranium salts in a drawer. Expecting faint or negligible results from unexposed uranium, he developed the plates as a control measure. To his astonishment, the plates exhibited a strong, clear image, demonstrating that the uranium emitted radiation even without prior exposure to sun. This unexpected result prompted Becquerel to fundamentally reconsider his initial assumptions. The radiation emitted by uranium was clearly independent of phosphorescence and did originate from an external energy source like sunlight. Instead, uranium itself seemed to be the source of this peculiar radiation, spontaneously emitting rays capable of penetrating opaque materials and affecting photographic. Becquerel presented his observations in a paper that challenged the very foundations of classical physics. The spontaneous emission of radiation from uranium defied established principles of energy emission and conservation. Prior to Becquerel's discovery, physicists believed that energy emission always required external stimulation or an internal chemical reaction. Uranium, however, appeared to be radiating energy without any apparent. The scientific community initially met Becquerel's findings with skepticism. The idea of spontaneous radiation emanating from a substance seemed almost preposterous, akin to perpetual motion, a concept long dismissed as physically impossible. Skeptics questioned the experimental methodology, suggested possible errors in the experimental setup, or proposed alternative explanations for the observed darkening of the photographic plates. Replicating Becquerel's findings became paramount. Despite the initial skepticism, the implications of Becquerel's discovery were profound. It suggested the existence of a previously unknown property of matter, a source of energy residing within the atom itself. This contradicted the prevailing view of the atom as an indivisible and immutable entity. Becquerel's work opened the door to a new realm of physics, one that would ultimately lead to the discovery of radioactivity, the nuclear model of the atom, and the harnessing of nuclear energy. The influence of Wilhelm Röntgen's discovery of X-rays on Becquerel's research is undeniable. Röntgen's work served as the initial catalyst, inspiring Becquerel to investigate whether phosphorescent materials emitted similar penetrating rays. Without Röntgen's groundbreaking discovery, Becquerel's line of inquiry might never have begun. Becquerel's discovery, in turn, directly influenced Marie and Pierre Curie. Intrigued by Becquerel's findings, the Curies began investigating other substances for similar properties. They meticulously analyzed various minerals, ultimately leading to the discovery of two new radioactive elements, polonium and radium. The Curies' work built directly upon Becquerel's foundation, expanding their understanding of radioactivity and paving the way for new avenues of risk. The observation that the intensity of the radiation was independent of the phosphorescence process carried immense weight. It invalidated Becquerel's initial hypothesis, forcing him to confront the existence of a new, unexplained phenomenon. This realization was crucial, since it disentangled the radiation from established process. The research then allowed a focus on the radiation's unique properties. Becquerel's willingness to abandon a favored hypothesis in the face of conflicting experimental evidence exemplifies the scientific method at its finest. Becquerel's 1896 paper, details a meticulous experimental methodology designed to investigate the nature of emissions from phosphorescent substances. Central to his approach was the use of potassium uranyl sulfate, a uranium salt known for its phosphorescent properties. Becquerel carefully prepared photographic plates, wrapping them in several layers of thick black paper to ensure complete darkness, thereby isolating any potential signal from external light sources. He then placed the uranium salt crystals on top of the wrapped plates and exposed the entire setup to sunlight, anticipating that the uranium would absorb the sun's energy, become phosphorescent and emit radiation capable of penetrating the black. Following the exposure, Becquerel developed the photographic plates, expecting to find an image corresponding to the shape of the uranium crystals. Initial results confirmed his hypothesis, showing darkened areas on the plates where the uranium salts had been placed. However, a pivotal moment arrived when Becquerel, preparing for further experiments, stored the uranium samples and wrapped photographic plates in a dark drawer due to inclement weather. He subsequently decided to develop these unexposed plates, expecting to find nothing or, at most, a very faint image. To his surprise, the developed plates revealed clear and distinct images of the uranium crystals, even though they received exposure only through the black paper without any exposure to sun. This unexpected result prompted Becquerel to conduct further investigations. He systematically varied several parameters, including the thickness of the black paper, the duration of exposure, and the type of uranium compounds used. These control experiments were crucial in enabling him to determine that the radiation emitted by uranium was independent of phosphorescence and external energy sources. He observed that the radiation continued to darken the photographic plates even when the uranium was kept in complete darkness for extended periods. An additional key observation involved the radiation's ability to discharge electrified bodies. Becquerel found that the radiation from uranium could neutralize the charge on an electroscope, an instrument used for detecting electrical charge. This finding was highly significant, as it indicated that the radiation was not simply light or other electromagnetic radiation. Instead, it possessed characteristics associated with charged particles, hinting at a deeper, atomic phenomenon. The cumulative evidence from Becquerel's experiments led to the revolutionary conclusion that uranium spontaneously emits a novel form of radiation, distinct from both light and phosphorescence, and emanating from the uranium itself. This discovery, initially met with skepticism within the scientific community, marked the birth of the field of radioactivity. Becquerel's careful experimental design, his meticulous observations, and his willingness to question his initial assumptions were instrumental in establishing the existence of this new phenomenon. Becquerel's work quickly resonated within the scientific community, most notably influencing Marie and Pierre Curie. Intrigued by Becquerel's findings, the Curies began investigating other substances for similar properties. They meticulously analyzed various minerals, ultimately leading to the discovery of two new radioactive elements, polonium and radium. The Curies' work built directly upon Becquerel's foundation, expanding the understanding of radioactivity and paving the way for new avenues of research. Becquerel's quantitative measurements of the ionization that uranium rays caused provided a crucial metric for the Curies' subsequent work on isolating and characterizing new radioactive elements. The observation that the intensity of the radiation was independent of the phosphorescence process carried immense weight. It invalidated Becquerel's initial hypothesis, forcing him to confront the existence of a new, unexplained phenomenon. This realization was crucial, since it disentangled the radiation from established processes. The research then allowed a focus on the radiation's unique properties. Becquerel's willingness to abandon a favored hypothesis in the face of conflicting experimental evidence exemplifies the scientific method at its finest. In conclusion, Antoine Henri Becquerel's 1896 paper represents a pivotal moment in the history of physics. Through meticulous experimentation and astute observation, he uncovered the phenomenon of spontaneous radioactivity. Becquerel's work initiated a paradigm shift in scientific understanding, paving the way for the development of nuclear physics, nuclear medicine, and nuclear energy. His legacy endures as a testament to the power of curiosity, driven research, and the transformative potential of challenging established paradigms.